In this presentation, we will go through a basic overview of the design and analysis of reinforced concrete shear walls. By the end of this presentation, you should be able to identify different classifications of shear walls, explain how the behavior will change according to classification, explain why shear and shear deformations are more critical in shear walls, analyze lineal shear walls to evaluate their flexural capacity, compare the behavior of lineal shear walls with uniformly distributed steel to those with steel concentrated at the ends, evaluate the shear capacity of lineal shear walls using ACI 318, and design lineal shear walls using the ACI 318 procedure. A shear wall is an element that can be used to resist lateral forces, and it essentially behaves like a really wide column. Shear walls need to have enough strength to resist the factored moments, shears, and axial loads acting on them, and they also need to have enough stiffness to limit lateral deflections. There are two ways to classify shear walls. They can be classified according to shape, which we'll go through on the next slides, or by behavior, which we'll also cover on the next slides. On the next few slides, we'll go through classification of shear walls according to shape. The most basic shear wall shape is a rectangular shear wall, or lineal wall. This wall is just a rectangular wall, and a system of rectangular walls can be used in a lateral force resisting system. Another type of shear wall is a flanged shear wall. It's similar to a rectangular shear wall, except you can concentrate reinforcement in the flanges at the end of the wall. So you'd have more flexural capacity in a flanged shear wall. More details on lineal shear walls and flanged shear walls are shown on this slide. You can see here that a system of lineal walls can be used in combination with columns as part of a lateral load resisting system. So here you have different walls in each direction to resist lateral loads in each direction. Here we have a flanged shear wall, and you can use flanged shear walls when you have a high moment demand on a wall or need increased ductility of your wall. So here we're concentrating reinforcement in the end, and we can add confinement reinforcement around our longitudinal reinforcement, which gives us additional ductility in our wall and a higher moment capacity. Two kind of subcategories of lineal shear walls are core walls, where we have a system of four lineal shear walls creating a kind of lateral load resisting core, which would typically be placed around an elevator or stairs. And then you can also have coupled shear walls, where you're essentially taking two lineal shear walls and coupling them together with these link beams in between. So the design of these link beams is important to make sure that a coupled shear wall behaves as one solid wall. The most common failure of these coupled shear walls is that these link beams fail, and then these walls behave as independent walls, so which dramatically decreases the stiffness of the system. So anyway, these are two subcategories of lineal shear walls. On this slide, you can see more details on the core wall and coupled shear wall systems. First, the core wall. You can see the core walls here around your elevator core. And essentially, these core walls can provide bidirectional lateral force resistance, so in both directions, placing walls around something you need to build anyway. So that's why this is one of the more common systems. The coupled shear walls, you can see the large amount of reinforcement needed in these coupling beams. So these coupling beams can be designed using the strut and tie method or using a common practice procedures, but you can see a large amount of reinforcement is needed to make sure that these adjacent walls behave as one larger wall. We can also have framed shear walls and infilled walls. Framed shear walls are essentially in a moment frame. You can fill in bays with concrete to create a shear wall essentially and stiffen up that one bay in your system. And we can also have infilled walls. So it's similar to a frame shear wall, only instead of filling in the bay with concrete, you're filling it in with masonry. Just note in both these systems, you need to make sure that you have the wall go the whole way to the top, or it needs to fill in the entire bay. If you only fill in part of the bay, then you end up with a short column, and that short column can become shear, or will be shear critical. So in these systems, just make sure that you fill up the entire bay with either masonry or concrete. On this slide, we can see some additional details for our framed shear walls and infilled walls. With the framed shear walls, we can use them to further stiffen or strengthen our moment frame. So you can see some framed shear walls in combination with our moment frame to further stiffen the system from lateral loads in both directions. So that direction and the other direction. You can see here they're symmetrically placed in this example, which we'll talk about later. Here you can see some infilled walls going in. So they're similar to framed shear walls, but they're less expensive in certain cases. So you can see the masonry going up and some of these infilled walls already completed. We can also classify our shear walls according to behavior. A shear wall is a shear wall where the deflections and strength are controlled by shear. This will be our least ductile of our shear walls. A moment shear wall is a shear wall where our deflections and strength are controlled by moment. So we'll have more ductility than a shear wall, but we can create a more ductile system where we'll have a ductile moment shear wall. In this case, this wall will have good energy dissipation characteristics under reverse cyclic loads. So when we're designing a wall to resist seismic loads, we want to try to create a ductile moment shear wall. For elastic behavior, any of these is okay, but if we expect or are designing for inelastic behavior, we want to make sure that we have a ductile moment shear wall. We will focus on lineal shear walls to start. These are the simplest, and then we'll see how these concepts can be used for other types of shear walls. Lineal walls are going to have a combination of flexure, shear, and rigid body deformations. When we were talking about columns, the deformation is dominated by flexure. When we have shear walls, our shear deformations and rigid body deformations are going to be more critical. So lineal walls have larger shear and rigid deformations than other members that we have looked at in the class so far. The type of deformation that's going to dominate our behavior of our walls will depend on the aspect ratio of the wall. In general, shorter walls are going to be controlled by shear deformations. So here you can see when we have a height to base ratio of 1, we have a ratio of our flexure to shear deformations less than 1. So here our deformations are controlled by, or the majority of our deformations are from shear deformations. As our aspect ratio increases, our deformations become more dominated by flexure. So generally a aspect ratio or H/B ratio of 2.5 is the border between where flexure and shear are going to control our walls. The stiffness of a shear wall is going to be dependent on the aspect ratio of the wall, or H/B. If we have an H/B greater than 3, our deflections will primarily be flexure, so we can use our flexural stiffnesses. ACI 318 allows us to use a stiffness of our wall, or of an uncracked wall, equal to 0.7 times the gross moment of inertia of the wall. For cracked shear walls, we decrease that stiffness by half. So our effective moment of inertia is equal to 0.35 I gross. When we have shorter shear walls, our deflections will also include shear deformations. ACI does not have an equation to estimate the stiffness when we have these short walls, but our white textbook has a modified moment of inertia equation that we can use to estimate the stiffness. So you can see that equation shown here. And you can see some of the properties and some of the terminology that we'll be using on the next couple slides, where HW is the height of the wall, LW is the length of the wall, and H is the thickness of the wall. The stiffness of a lineal wall can be estimated by considering the wall as a vertical cantilever with a constant EI over the height, loaded with a constant wind over the height. In actuality, the wind won't be applied as a constant load over the height of the wall, but just for simplicity, we'll assume it is here. So there will be some slope in the deflected shear wall that will be the greatest at the top, this delta top. And we'll use this to help to approximate the total drift that we have. And we can compare that total drift with a typically used limit of height of the wall over 500. Note that there's no drift limit currently specified in ACI or ASCE, but ASCE 710 does say that lateral deflection or drift of structures and deformations of horizontal diaphragms and bracing systems due to wind effects shall not impair the serviceability of the structure. So a typical limit to ensure that our lateral deformations don't impair the serviceability of the structure is this HW over 500 limit. Using this drift limit, we can then determine the total stiffness of the walls in the direction of the wind. So we can take the summation of all of the wall stiffnesses. Here I'm assuming that all of our walls are uncracked, and make sure that that stiffness is greater than this value here, which is derived based on the two equations that we had on the previous slide. So we can then lay out our walls in each direction. So we'll need to design for wind in both directions, and make sure that we have enough stiffness to limit the deformations. On the next couple slides, we're going to be going through how to find the flexural capacity of our lineal walls. Generally in these walls, we're going to have reinforcement spaced evenly over the length of the wall. So here in this example, we have a 12-inch thick wall with number 4 bars spaced at 12 inches in each direction. So that means we have number 4 bars spaced at 12 inches in the vertical direction that will contribute to our flexural capacity. What we can do is we can group this reinforcement into different layers to simplify our analysis. So here I'm grouping 3 bars into one layer. So we will have one group of number 4 bars here at 36 inches, one at the center, and then on the other side spaced at 36 inches. We can, at ACI 318 tells us that we can use procedures or a procedure similar to columns to analyze our walls. So that's what we'll do on the next couple slides. We'll need to solve for the stress, the strain, and the force in each layer, just like we did for columns. So we can first solve for the strain in the columns, assuming that we have a compression strain at the extreme compression fiber of 0.003. So the same assumption that we made for our beams and our columns, we're going to make in our walls. One difference is that if we're using longitudinal reinforcement without confining steel around it, so here we have the bars spaced evenly at 12 inches and we don't have any confining steel around it, we're going to assume that we will neglect the compression steel. So we'll assume that any steel with a compression strain will buckle. So we're going to neglect that from our calculations. So from our strain diagram, we can go to our stress and our force diagram. We can calculate use the strain in each layer of steel to calculate the stress in each layer of steel. which we use to calculate the force in each layer of steel. And again, the difference is that all of our compression steel, we're going to assume has a force equal to 0. The compression region of our concrete will assume the same stress block assumptions that we did for flexure and for our columns. So we have a compression block depth of A equal to beta 1c, and where c is our neutral axis, and we can solve for our neutral axis based on equilibrium. And the height of the compression block is just 0.85 f prime c, so the same as beams and the same as columns. The easiest thing to do here is to set up a spreadsheet because you have so many layers of steel. On the next couple slides, I'm going to go through a spreadsheet that I set up for this. Shown on this slide is a sample of part of the spreadsheet that I developed for this. And if you want to know more details on the specifics of going from strain to stress and stress to force, I'd suggest you go back and look at our section on columns and our section on beams. So you can see for each layer we have an area, we have a depth of the layer, we have a yield strength for the layer, and we have a yield strength for the layer in compression. So here I'm saying that the steel's not confined, so if we have a compression stress greater than 0, we're going to take that as 0. So here, for each layer, we have the strain in the layer, we have the stress in the layer, which is just the strain in the layer times the modulus for the steel, 29,000 KSI. And then we have the force in the layer, which is just the stress in the steel times the area in the steel. So then note here that the stress in the steel, I have an upper limit of 60 KSI for tension and a lower limit of 0 if we're in compression. So here in layer 1, we have a compression strain, so we have 0 stress. And because we have 0 stress, we have 0 force. So then the total force in the column will just be equal to the summation of all of the forces of all of our layers and also the force from our concrete. And we can also find our moment by just taking our force times the lever arm of each force, and we'll sum moment about the plastic centroid of our wall. Using the principles from the previous slides, we can develop the moment axial force interaction diagram for our wall. You can see the moment axial force interaction diagram for the wall that we've been looking at is shown here. You can see that because we have the reinforcement spaced evenly out over the wall, we're going to have a lower flexural capacity. So a lower pure flexural capacity, and most of the diagram is going to be on the compression side of our diagram here. So if we had more reinforcement grouped at the ends and we provided confinement steel around that reinforcement, this diagram would be shifted more down into the tension side, and it would look more like a column. But anyway, this is kind of a typical moment axial force interaction diagram for a lineal shear wall. Steel in our lineal shear walls can either be distributed uniformly along the wall or can be concentrated at the end. So either distributed uniformly along the wall or concentrated at the end. And if it's concentrated at the end, typically you'll provide confinement reinforcement around that steel. So listed on this slide are some of the benefits of each, the pros and cons for each type of wall. In general, distributing steel uniformly is going to give you almost as much strength as concentrating it at the ends. It'll give you, typically it'll give you sufficient ductility. We'll have less buckling of the bars at the ends because we're not relying on it. We'll have less splitting at our wall toe, the end of the walls, and we'll also have more clamping and more sliding shear capacity along the length of the wall because of the evenly distributed steel. Concentrating the steel at the end will give you slightly greater strength because you have more steel at the end with the largest lever arm. It'll give you greater ductility because you are providing confinement reinforcement around that steel. So you're confining the steel and preventing the longitudinal steel in the ends from buckling. You can have buckling of the bars at the end if you don't provide sufficient confinement. You can also have splitting of the wall toe if you don't have sufficient confinement reinforcement. And you have less sliding shear capacity because you have less steel spread out over the length of the wall. So generally you can design a wall sufficiently by distributing the steel uniformly along the length. If you do decide to concentrate the steel at the ends, you can provide a barbell design at the end of the wall. And this will give you more room to provide your confinement steel and more room for your longitudinal steel in the end region as well. So this is kind of like our flanged shear wall shape. On the next few slides, we're going to look at how to calculate the shear in our lineal shear walls. So as previously discussed, cracking is either going to start in the web of the wall and expand, which would be web shear, shown on the left, or it's going to begin as a flexure crack and turn into a shear crack, or flexure shear cracking, shown on the right. Typically, whether you have web shear cracking or flexure shear cracking is going to depend on your aspect ratio. So if you have an aspect ratio, or HW over LW, less than 2, it's a short wall and you'll be dominated by web shear cracking behavior. If you have an HW over LW greater than 2, then you'll have a flexure shear cracking, and you'll have the cracking shown on the right. The ACI 318 expressions account for both types of shear. The equation for estimating the nominal shear capacity for shear walls from ACI 318 is shown on this slide right here. This equation was modified from ACI 318.14 and earlier to the equation shown to be more consistent with the seismic equations found in chapter 18. So you can see the equation depends on this alpha C factor, which depends on the aspect ratio of our wall and whether we have net axial compression or net axial tension. The lambda factor, which takes into account whether we have lightweight or normal weight concrete. Our shear strength, our concrete compressive strength, so square root F prime C, which was common for our shear expressions. And then it also includes in this equation the benefits that we get from our transverse steel. So we have rho T, our transverse reinforcement, FYT, the yield strength of our transverse reinforcement, and then all this times ACV, where this ACV is the gross area of our concrete section bounded by the web thickness and the length of the section in the direction of the shear force. So this just means that it's the length of our wall times our wall thickness, and that's how we get our ACV. The alpha C factor depends on the aspect ratio of our wall. So for shorter walls, we use a lambda C factor of 3. If we're between 1.5 and 2, then we use a transition equation that's shown here that includes the aspect ratio HW over LW. And if we have flexure shear and an HW over LW greater than or equal to 2, then our alpha C is equal to 2. And note that all these alphas here are if we have net axial compression on the wall, which will typically be the case for us. Note also there's an upper limit to our VN. So note that our VN needs to be less than or equal to 8 times the square root of F prime C times ACV. Also shown on this slide is the alpha C factor if we have net axial tension. So if we have net axial tension where NU, our axial load on the wall, is negative for tension, we can calculate our alpha using this expression, making sure that our alpha is greater than or equal to 0. ACI also provides an alternate procedure for web shear. So if we have web shear that's going to control failure, or a low aspect ratio, HW over LW less than 2, ACI 318 permits us to use the strut and tie method procedure that's provided in Chapter 23. So again, the short aspect ratio means that we have a deep beam or disturbed region, which means that we can use the strut and tie method procedure. We account for the shear strength provided by the transverse reinforcement using rho T, or the transverse reinforcement ratio. So this rho T is equal to the area of our transverse reinforcement divided by the spacing of the transverse reinforcement times H. So AV over S times H. And we can calculate that and plug that into our VN equation. Note that only the horizontal reinforcement counts or may be counted as your shear reinforcement. So you also have vertical reinforcement, and the vertical reinforcement is your primary kind of longitudinal reinforcement, but that doesn't count here for your shear reinforcement. I also show on this slide the maximum spacing requirement for our horizontal reinforcement. So we need to space this reinforcement less than or equal to the minimum of 3 times H, our wall thickness, and 18 inches. ACI 318 also has minimum transverse steel reinforcement requirements that are shown on this slide. And these requirements depend on the shear demand on the wall. If you have a low shear demand, so a V sub U less than or equal to 0.5 phi times alpha C lambda square root F prime C times ACV, then you can use the values or the minimum transverse steel requirements shown in this table 11.6.1. You can see the table breaks things up based on the wall type, the type of non-pre-stress reinforcement, the bar or wire size, and the yield strength of that reinforcement. So whether you're less than or greater than 60 KSI. And then you have minimum longitudinal and minimum transverse reinforcement requirements. If you have a high shear demand on your wall, then your minimum transverse reinforcement requirements increase, and so do your minimum longitudinal requirements. So you can see those requirements here at the bottom. On the next couple slides, we're going to go through how to design lineal shear walls. The first step is to come up with your preliminary sizing and layout of your walls. Typically, you want to locate your walls in the center half of the building. This is a good location for resisting lateral loads. Locating the walls in the ends of the building can also increase your slab restraint and your shrinkage stresses, which can be an issue for long buildings or buildings exposed to large temperature changes, such as parking garages. Two additional factors that you want to consider when laying out your shear walls are shown on this slide. First, you want to try to arrange your walls symmetrically to avoid designing your walls for torsion. So shown here are two symmetric arrangements of your walls. So you want symmetry of your building in plan about both axes. So here you can see the walls, and in both cases you have a symmetrical layout. Next, if you are resisting torsion, then perimeter walls are the most effective at resisting these torsional forces. So if for some reason you do have torsion on your building, you'd want to put your walls around the outside of the building to be most effective at resisting these torsional forces. The initial thickness of the wall can be determined based on the minimum thickness requirements from ACI 318. So those are shown in this table based on whether it's a bearing wall, a non-bearing wall, or an exterior basement foundation. Typically, a 12-inch wall thickness is a good place to start. So for the example in this problem, we had a 12-inch wall thickness, and most of the time using a 12-inch wall is a good starting point for you. With the 12-inch wall thickness, we can then determine the total number and length of shear walls in each direction using the equation that we came up with earlier in the class. So we want to provide enough walls in each direction such that we have sufficient stiffness of our walls. So we can sum the 0.7 I gross of all of our walls in one direction and make sure that it's greater than or equal to this equation here, 500 WS, our wind load, times HW to the third, the height of the wall to the third, divided by 6 EC. So remember that this is an estimate that assumes that the wind load is constant over the entire height of the wall. This isn't true. So this is just a preliminary design equation. And it also doesn't include any torsional loading on the structure. So you will need to go back and check your actual drift at the end. Our next step is to determine what type of diaphragm we have. A diaphragm is the element in a structure that distributes the shear and the moment to all the walls. So we're distributing all of our shear from our applied load into our shear walls in that direction. We can either have a flexible or a rigid diaphragm, and this is based on the amount of deflection that occurs in the diaphragm. A diaphragm is considered flexible if the maximum diaphragm deflection, delta D, is more than twice the average drift of the vertical element. For flexible diaphragms, we just use our tributary area concept to distribute shear, and we don't consider any torsional effects. So here we have shear walls on the outside, so our tributary area would be half of our width, so half of this shear and moment would go into these two walls on the outside of the structure, and half would go to the other two walls. If you have a rigid diaphragm, then the shear needs to be distributed amongst the walls based on the rigidity of the wall. Our shear rigidity of the walls given by this equation, EA over L, and we can plug in the specifics for our A, the length of the wall times the thickness of the wall, and our L, the height of the wall, H sub W. Typically all walls will have the same height and the same concrete stiffness, so you can eliminate some of these terms. I'll keep it in here just for completeness. So in this example, the four walls are going to contribute to the resistance of the wind load in the horizontal direction. So 1, 2, 3, 4 walls that are perpendicular to the wall load or the wind load are going to resist the shear in that direction. And each of these walls is going to take a portion of the load based on the shear rigidity. So rigidity R. We can determine the shear by taking the total shear, our WS times the width of the structure, B, and then take that times the rigidity of our wall 1 divided by the total rigidity of all of our walls, or the summation of our R sub i's. So this is how we would determine the shear that goes into our wall number 1. If there are no torsional effects, then we can distribute the moment that the wind causes on the structure to the walls in a similar fashion. If there are torsional effects, then we need to use some type of 3D model or a structural analysis software. If we don't have a symmetrical wall arrangement, then we need to calculate the center of rigidity and add an additional shear caused by the torsion of the structure. The center of rigidity we can calculate in each direction by taking the distance from one side to the center of the wall times the area of the wall, and then divide it by just the area of the wall. And this is assuming that we have the same height and same concrete stiffness, or else we would include those in the rigidity term that we had on the last slide. So then we can do the same thing in the x direction. So you can see the center of rigidity is going to be pulled towards the more rigid side. So in our y direction here, we have two walls on the lower side and only one wall on the top. So the center of rigidity is pulled down. And in the vertical direction here, we have one wall further to the right than this wall. So the center of rigidity is pulled to the right towards this other wall. Then using these, we can find our polar moment of inertia of our shear wall system. So our I sub P is just the length of the wall times the thickness of the wall times the distance between the center of the wall and the center of rigidity squared. And you sum all these for all of the different walls in both directions. And that's how you get your polar moment of inertia, which we'll use on the next slide. The distance between the center of the wind load or seismic load and the center of rigidity is going to cause a torsional moment on the building. This distance can be calculated as shown here for non-seismic, and for seismic, they want you to add an additional 0.0, or ASC 7 requires that you add an additional 0.05 times the width of the building. So you'll have an additional load, which will increase your torsional effects. So your torsional moment then is just your total wind load times this distance causing torsion. And our torsional shear, we can then distribute to each wall as shown here. So each wall, V sub I, is going to get an additional shear caused by the torsional effect. And we divide by the polar moment of inertia that we found on the previous slide. And note that this torsional shear on each wall is in addition to the shear caused by the wind force. So the shear that we found a couple slides ago will be added to this torsional shear. After we determine the demand on each individual wall, we can continue by detailing our flexural reinforcement in each wall. We want to proportion our reinforcement using our ordinary flexural theories described above, and this is when we can also decide whether we want to distribute the primary flexural reinforcement along the entire length of the wall, or if we want to group the reinforcement at the ends and or create more of a barbell shape or flanged shear wall. So if you have a high moment demand, then you want to think about grouping the reinforcement. Otherwise, you can distribute the reinforcement along the length. We also, at this point, should check our spacing limitations for our vertical reinforcement. So you can see the spacing requirement from ACI here, where our spacing needs to be less than or equal to 3H, 18 inches, and LW over 3. There is a minimum amount of vertical reinforcement. So our rho L, which we'll look at on the next slides, but we'll check this when we look at our vertical shear reinforcement. Our next step is to determine the horizontal shear reinforcement that we require. So in this case, we need to make sure that our phi Vn is greater than Vu for each of our walls. And we can determine our Vn using the equation from ACI 318. So here we can determine what our aspect ratio is for our walls and determine our alpha factor, come up with we know our concrete strength for our wall and whether we're using lightweight or normal weight concrete. And we know the area of our wall. So we can use this equation then to determine the reinforcement ratio, or rho T, required to resist the shear applied to each wall. Using these equations, so using our phi Vn greater than Vu and our expression for Vn, we can solve for the required horizontal reinforcement. And we can compare this value then with the minimum transverse reinforcement ratio that's required by ACI 318. Our minimum shear reinforcement required, or minimum transverse reinforcement ratios required by ACI 318 are shown on this slide, where if we have a lower shear demand, so VU less than or equal to 0.5 phi VC, then we have a smaller transverse reinforcement required. So if we have number 5 bar or less than number 5 bars with a yield strength equal to 60 KSI, which will be most often the case, we'll have a required reinforcement ratio greater than or equal to 0.002. If we have a higher shear demand, then this increases. So for all cases, if we have a VU greater than our 0.5 phi VC, then our rho T needs to be greater than or equal to 0.0025. Our maximum spacing limit is also shown here from ACI 318, where our S sub H, the spacing of our horizontal reinforcement, needs to be less than or equal to 3 times our wall thickness H, 18 inches, or LW, the length of our wall, over 5. The minimum vertical shear requirement is shown on this slide, and this reinforcement will typically also be our primary longitudinal steel in our wall. But you can see it depends on whether we have low shear demand or high shear demand, same as our horizontal shear reinforcement, and also our bar size and yield strength of our steel. So typically we'll have number 5 or less than or equal to number 5 bars with a yield strength of 60 KSI. So we'll have a rho L that needs to be greater than or equal to 0.0012. And you can see how to calculate your rho L, which is our area of our vertical reinforcement, divided by the spacing of that reinforcement times the thickness of our wall. You can also see for higher shear demands, so V sub U greater than 0.5 phi VC, we'll need a higher reinforcement ratio for our longitudinal steel or our vertical shear reinforcement. So you can calculate that using these equations shown here. The last item we need to check is the spacing of our vertical steel. So our spacing requirement in ACI 318 is shown here. So SV less than or equal to 3H, 18 inches, and the length of the wall LW divided by 3. So at this point, we've designed our wall to resist moment and shear, and we've laid out the walls such that we provided, I guess, the approximate required stiffness to resist our lateral loads. So that concludes the general design procedure for shear walls. Some additional references on shear walls are shown on this slide. And that concludes this presentation on the analysis and design of reinforced concrete shear walls.